Welcome to today's Explainer. We're diving headfirst into the completely mind-bending phenomenon of quantum entanglement. We're going to look at exactly how this one, singular, absolutely baffling concept just shatters our most deeply embedded assumptions about the universe. So let's get right into it.
The universe is 13.8 billion years old, vast, ancient, and mostly invisible. And somewhere out there are answers to questions that keep scientists awake at night. Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown. This is space like you've never seen it before.
Let me start by asking you something a bit provocative. Because honestly, by the end of this explainer, you might just realize that your basic intuition about the physical world has been completely deceiving you. You see, for centuries, our perception of reality has been built on this very specific foundation, and quantum mechanics is about to completely tear that foundation apart.
Section 1. The classical reality illusion. To actually get why this stuff is so terrifying to physicists, we first need to establish that comfortable, everyday baseline that we all instinctively believe in.
See, our everyday lives are built on this quiet background assumption known as local realism. It's basically the idea that, hey, a cup sits on a table whether you're looking at it or not, right? And that distance is a real, tangible separator. Causes propagate through space over time. Nothing can just magically influence something else instantly from a distance. We just assume reality is objective, stable, and completely external to us.
And the contrast here is incredibly stark. Classical physics gave us a really stable world, like a vast, precise Newtonian machine, where every single thing has a definite position and a predictable future. But quantum mechanics dismantles that entire machine. It tells us that, at the deepest level, particles don't even have a single fixed property. Instead, fundamental reality is made up of unresolved potentials. It's just a range of unstable probabilities, all hovering in superposition until they're actually measured.
Section 2. The Quantum Entanglement Glitch. Okay, let's explore the actual glitch in the matrix, the exact spot where our everyday intuition just completely breaks down and things get remarkably strange.
Just think about how deep this weirdness actually goes when you look at a simple coin toss. In normal everyday life, uncertainty is really just a lack of knowledge. You flip a regular coin, slap it on your wrist, and it's already heads or tails, right? You just don't know it yet. But a quantum coin toss, that coin genuinely exists as both heads and tails simultaneously. It's in a superposition. The outcome isn't just hidden, it is genuinely unresolved until you look.
Now here's the kicker. Entangled particles do not behave like simple everyday objects. You'll often hear this glove analogy for entanglement. You put one glove in a box, ship it across the world, open your box, see a left glove, and boom, you instantly know the distant one is the right glove. But wait, that was predetermined. Quantum entanglement has no hidden labels. Both particles stay in that fuzzy, unresolved superposition. And yet, the literal microsecond you measure one particle's spin, it instantly forces the other into the opposite state, across vast distances, with absolutely zero time delay. Crazy, right?
Section 3. Einstein's spooky action. This absolute, blatant violation of local realism deeply, deeply troubled some of the most brilliant minds in history, and it sparked a desperate defense of reality itself.
Albert Einstein famously called this spooky action at a distance, and he wasn't trying to be poetic here. This was a frank, pointed criticism. He was essentially arguing that reality just couldn't be built from independent parts if physical distance meant absolutely nothing. To Einstein, this instant correlation meant quantum mechanics simply had to be incomplete. He just could not accept that space itself could lose its fundamental meaning as a separator of objects. This whole thing kicked off a historic scientific detective hunt that took decades to unfold. Back in 1935, Einstein, Podolsky, and Rosen published the famous EPR paper to formalize these concerns. And for a long time, it was mostly just a philosophical debate. But then, jump to 1964, and physicist John Bell formulates a brilliant mathematical limit known as Bell's inequality. By the 1970s, we finally had the first precise experiments to test this non-locality in the lab. We literally turned abstract philosophy into hard, empirical science.
This entire era of physics was really defined by one massive core conflict. On one side, does the universe have hidden layers of information? These are Einstein's hidden variables, the idea that particles carry unseen, predetermined instructions that preserve objective reality and locality. Or was Niels Bohr right? His active measurement idea argued that the measurement itself defines the properties. To Bohr, asking what the particle was doing before you looked was just a totally invalid question.
Section 4. John Bell's reality test. The absolute climax of this scientific showdown arrived when John Bell finally figured out a way to empirically test these two completely opposing views of the universe. So, the experiments are run, and guess what? Bell's inequality was violated. The universe officially, mathematically, rejected Einstein's predetermined instructions, those local hidden variables, which were really the very last refuge for our classical, common-sense intuition. They just do not exist. Period. These experiments proved once and for all that the universe is fundamentally non-local.
And this gives us the truly mind-bending truth of our reality. It's not like particles are secretly whispering faster-than-light messages to each other. No, it's that asking how one particle influences the other is literally the wrong question to ask. They are actually components of a single unified system, totally regardless of distance. Space and separation, they just aren't fundamental at the quantum level. It is one system, simultaneously expressing itself in two different locations.
Section 5. The decoherence effect. Now, at this point, you are probably wondering, okay, if the quantum world is this chaotic and non-local, how does that translate into the solid, stable world that we walk around in every single day?
Like, if the universe is fundamentally quantum and entangled, why does my table feel so completely solid? It's a completely natural question. Why aren't everyday objects glitching out? Well, the answer lies in an incredibly fascinating process that effectively masks all that underlying weirdness from our everyday view.
The secret here is a process called decoherence. Imagine a delicate quantum system existing in this isolated superposition. But then, it starts interacting with environmental noise, stuff like air molecules or thermal radiation. As it does that, the quantum entanglement essentially dilutes outwardly across countless degrees of freedom. So all that constant messy interaction effectively averages out the quantum weirdness, leaving us with the stable, predictable, classical behavior that we actually experience.
Think of decoherence exactly like trying to hear your friend whisper in a crowded, noisy room. The quantum signal is absolutely there, but it is just hopelessly overwhelmed by environmental background noise. What this means is that our classical, predictable world, it isn't some separate reality. It's actually just a byproduct. It's quantum entanglement spreading way beyond our human ability to observe it.
Section 6. Redefining our universe. Now that we've seen exactly how reality hides its true quantum nature, we really have to rethink our fundamental approach to knowledge and, well, to existence itself.
This forces us to accept a pretty shocking new framework. Reality is actually a continuous unfolding of interactions, not some fixed structure. In quantum mechanics, relationships exist first, and objects are just derived from those relationships. You see, the human brain's shortcuts for efficiency, the way we evolved to isolate variables and categorize a stable world, they completely fail at the quantum level. Understanding the whole doesn't mean you can just break it down into parts anymore.
Physicist Leonard Susskind points this out beautifully. He notes that with an entangled system, you can know absolutely everything about the whole system and still know nothing about its individual components. It totally reverses our everyday logic. It introduces this profound level of ignorance that literally no scientific instrument will ever be able to resolve, because the individual particle remains entirely undefined until measured. So, I'm going to leave you with this final provocative thought. Our intuition practically demands a world of isolated, understandable objects, right? But quantum mechanics hasn't destroyed reality. It has simply revealed that the predictable, tick-tock machine we've always believed in was only ever just the surface. So the question is, are we actually ready to accept a reality built on relationships instead of isolated objects? Thank you so much for joining me in this explainer, and hey, keep questioning everything you see.
If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then, stay curious and keep looking up.